Grobman.
Hey, good evening. It's really great to be back at NC State. It has been 25 years, so it's great to be back home. What I am going to do this evening is talk about how in the security industry we're using artificial intelligence as really the foundation for really all of our products. But one of the things that we have to recognize is the technology does have a dark side. We really do need to understand it. And it's not something that's new to just artificial intelligence. It's actually something that technology has had really throughout its history. I mean, given that we're here in North Carolina, it would be fitting to start with the technology of flight. And if you think about what flight has done for humanity, it's totally changed the way that humans live. So we can now move between continents in hours as compared to days or weeks. Now, if you think about the way that all of our economies and businesses operate, everything's global. But that exact same technology has also really changed the impact of war. So in World War II, we saw over 2 million casualties that were caused by the invention of air power and tremendous destruction beyond things that we'd seen in any other conflict. So if you put all the pieces together, at the end of World War II in 1948, Orville Wright was still alive, and he was asked about his invention after seeing all of this destruction. And the question was, Orville, do you regret inventing the airplane? And what Orville said was that he didn't, because technologies can be used for good or bad. And it's a lot like fire, where yes, it can cause tremendous harm, but it's also can be put to many important uses. And it's that insight that will really be what we talk through with modern technology. So if we pivot into my primary domain, which is cybersecurity, one of the areas that we have this dual use of technology is encryption. So for the comp sci people in the audience, you should recognize this algorithm. It's RSA. But think about it this way. The RSA algorithm is the exact same algorithm that can be used to protect data from theft or hold individuals for ransom, right? And if you think about the scale that we use this technology today, every month we're encrypting 156 exabytes of data on the web every month. But at the same time, we're seeing really a level of ransomware in the consumers and in organizations and in businesses beyond anything that we've ever seen in the past. And this debate is not new. So something that right when I got out of NC State and kind of went out into industry, it was the 90s. And there was actually this debate on whether you could control the use of encryption. So they called it conditional use. And a lot of government proponents were pushing for actually treating encryption as a munition. So there was a law that it was illegal in the 1990s to export software that had encryption. And the US government actually classified it as a munition, just as if you were shipping bombs or bullets or other ordnance. So you had to be very careful as a software developer, because simply doing essentially math could make you a weapons provider to the industry, and you could end up, potentially in the custody of the FBI. So it was this big debate that we had in the 90s, and just as today when there are controversial issues, there were forms of civil disobedience. So there's a large conference that the cybersecurity industry holds every year called the RSA conference, and back in the 90s, people would actually wear shirts that looked like this. And essentially what the shirt was is it had a minimal implementation of encryption, really calling out the absurdity of the US government regulation, where by having a bare bones implementation of encryption, they were saying, hey, my shirt is classified as a munition, and it's illegal to even show this to a foreign national. The good news, and all of you can go back and write some code and ship it off and not worry about going to jail, because in the end of the 90s, they actually figured out this made no sense. At the end of the day, encryption is just math, and you can't stop someone from doing math. So you have to recognize that encryption will be used for good, it will be used for evil, but at the end of the day, it's technology that exists and can be used for a wide range of purposes. So when we pivot a little bit, and I'll get into really the heart of what I want to talk about for the most of this evening, which is artificial intelligence. We hear a lot about artificial intelligence. I'm sure many of you have taken classes in AI and machine learning and other forms of data science. But one of the challenges that we have in the industry is it's often positioned as this silver bullet that can solve any problem, and the nuance that's required to understand its limitations are often not looked at to the degree that it really needs to be. And one of the things that I try to make clear is the field of AI doesn't have to be complicated in many purposes. Sometimes to build an effective model, so if you think about what artificial intelligence or machine learning is largely about, it's about building models that are able to take inputs and then predict an output. So if we look at a really simple example, and I know there are some non-computer science folks in the room, I wanted to build a really simple model. And I do this to show a model does not have to be complex. So if I wanted to build a model in order to predict, is an Olympian a volleyball player? So think of it as you've got all of the Olympians for the 2022 Olympics. They're all standing outside, and we're going to march them through. And we don't know what sport they play, but we want to build a model that basically says, are you a volleyball player? You can use all sorts of fancy things, but a model that actually works pretty well is one line of code. It's, are you taller than 6 feet tall? And if you use the model, are you taller than 6 feet tall, it'll actually correctly identify 71% of the volleyball players as volleyball players. You won't get them all. This is one of the public data sets, I think from the 1996 Olympics, or it might have been 2000. But there were people like Salima Hamouche at 5'2", Olympian volleyball player. And then clearly the problem is, well, what about the people that are taller than 6 feet tall that are not volleyball players? And the nomenclature there is, well, those would be false positives. Those would be people that we've identified as a volleyball player, but they're not. So our basketball players are going to be incorrectly identified. What's interesting about this simplistic model is it's actually pretty good, because our false positive rate is only 27%, while we're getting a true positive rate of 71%. And the reason I like using this example is it also lets you understand how you can adjust the sensitivity of a model very easily, and also what the consequences of that adjustment are. So for example, if I challenged you to use this model to detect a higher percent of volleyball players, what would you do? Well, you would simply just slide this red line to the left, right? And now you're going to get more of the volleyball players to the right side of that red line. So you can set the sensitivity of the model to detect any percentage of volleyball players you want. Clearly the challenge being, as you start sliding this red line to the left, you're also going to start detecting a lot more people, a lot more athletes that are not really volleyball players as being volleyball players. So this is really just to introduce how simple a model can be. When we get to the next level and think about a little bit of the taxonomy of how we're looking at data science and artificial intelligence, three of the very large areas are AI as a field, and the way that I think about it is artificial intelligence is really using any form of intelligent machine capability. It can be for automation, it can be for predictive analytics, and then a lot of the fields are now focused on specific elements. So machine learning, where you're training a model based on things that you've seen in the past. And then a sub-element of that, deep learning, using a specialized form of machine learning where you're typically using things like deep neural networks. But the models themselves aren't any good unless you have data. And one of the other interesting things that we see is in 2019, there's immense quantities of public data available for open analysis. So when I gave a version of this talk a few weeks ago, it was out of San Francisco, and we checked, what sort of data does the city of San Francisco make available for open analysis? And it turns out that if you go to datasf.org/open data, there's over 400 data sets on energy, on all sorts of fields, including things like public safety. So what we did is we started thinking about, how can you use this new field and the new techniques around AI and machine learning with publicly available data for good? And there's a lot that you can do to make the world a better place by using this technology on this open data. So for example, you can optimize where police will focus their patrols. You can identify hotspots of crime in order to have citizen training in those areas, really making the city safer. But what we also recognized is the exact same data could be used by a criminal to make them a better criminal. And we did that too. So with 50 lines of Python and a machine learning library out of Spark, we built a model that would basically predict whether or not a cyber criminal would get arrested based on parameters of a crime. And even with a very simplistic model, we were able to come up with a pretty good model. So what we see here on the left is, if you've taken a machine learning class, it's a ROC curve. It essentially plots the false positive rate versus the true positive rate. And if you think back to my volleyball example where I said you could slide that red line to anywhere on the chart from a sensitivity perspective, you can do the exact same thing with this model as a criminal. So think of it as the further to the left that they go on this chart is going to decrease the number of opportunities that they have to commit crime for specific parameters, but they're less likely to get caught. And then the further to the right they go, they'll basically have a lot more opportunity to commit crime, but they'll also increase their probability that the model is predicting them not being arrested, but they actually do get arrested. So recognizing, just like the other technologies, the underlying artificial intelligence or machine learning in this case that is figuring out whether or not a criminal is going to be arrested, it's just math and doesn't necessarily know that it's doing something good or bad. So it gets us thinking, what are some of the other areas that artificial intelligence could be used by an adversary in order to make their techniques more effective? And one of the things that's a hot topic today is deepfake videos. So if you think about the use of AI for information warfare, so me and my colleague that co-presented at this talk, we literally put together this fairly crude video in a weekend. And I'll go ahead and play it, and hopefully the sound works.
Unfortunately, AI is well suited to generate false content that's highly believable. For example, deepfake video can create realistic footage that is 100% fabricated, making it appear that individuals are making statements or involved in activities that have not occurred.
Okay, so it's not perfect. And if you look, there's some artifacts. If you actually look at it frame by frame, you could detect that that was a deep fake. What I think is more interesting is how easy it was to build this. So as I mentioned, we did this all with open source software. We wrote a little bit of Python in order to do some of the compositing, but it literally took a weekend to get to that state. And we learned a lot. Like everything else in engineering, when you do something once, you learn a ton and you would do it better the next time. One of the challenges that we had in making it glitch-free was me and my co-presenter were fairly different from a physical characteristic perspective. So getting everything to match was difficult, whereas if you used an actor that was the same gender, more similar in features to myself, it would have looked more believable. And here's essentially the recipe that we used. So we went out and we just Googled, very high tech. We Googled, what are the different open source deepfake video creation capabilities that are available. One of them that we found, I forget exactly which one we ended up going with. It was IPEROV, Deep Face Lab. And so we used that, and then we had to get both source and target videos. So what we wanted to do in this case was show that you can use pre-recorded content. So we went way back to 2017 to some comments that I had made publicly that were already on the web, and we grabbed those to show you can build something off of video that already exists from the distant past. So then my colleague went ahead and recorded the words that you heard me talk. We then used the open source deepfake application to train the video. Because of the challenges that I talked about, we did use some custom compositing. So on the video, you saw the face tracking markers. What we actually did is we tracked basically both of our mouths, chin and nose, and took the AI built image and then composited that onto the source image in order to get them to match with the right mouth expressions for each part of the video. And one of the things that I really want to point out here is this adversarial use of machine learning is going to make our adversaries more effective. If you think about my field of cybersecurity, it's not just a technology problem. A big part of the problem is the human factor, where many cyber attacks start as phishing. So convincing somebody that they should click on something, or convincing somebody that something that is not real is real. And deepfake videos is just one area that AI will help. Another area is in the automation of targeted content for phishing attacks. So if you think about what a cyber attacker had to do in the good old days, they could essentially choose, do they want to do a mass phishing campaign where they send out 1 million emails to 1 million individuals that are all identical? It'd say something like, a package has been shipped to you, here's the UPS link, click on the link to track your package. And the problem with those is they would have a fairly low victim conversion rate. Or they could do spear phishing, where they would research an individual, find out information about their background, and then send them a very targeted email with information that was very pertinent to them. Hey, I know you went to this lecture on Tuesday evening. It was great meeting you. You mentioned a really cool application to download. Here it is. What AI does in this case is it allows an adversary to have the scale of traditional phishing, but with the ability to target close to spear phishing. So essentially use automation of targeted content in order to get a higher victim conversion rate. So one of the other things that we're trying to point out in the cybersecurity industry is when you use AI for cybersecurity, it is different than using AI in other fields of computer science. So if you think about using machine learning to track hurricanes, when you get good at tracking hurricanes, it's not like the hurricanes all of a sudden change the way they operate. It's not like the laws of physics change and water evaporates differently. But in cybersecurity, that's actually exactly what happens. So we're studying this new field called adversarial machine learning, which is the technology behind confusing machine learning algorithms. And let's start with a simple example with image classification. So what we started with here is an image on the left of a rockhopper penguin. And when we run that through one of the standard image classifiers, it correctly classifies it as a rockhopper penguin with a confidence of 99 point whatever that is %. Using adversarial machine learning, we can figure out the minimal changes to the image in order to make the machine learning model completely fall apart. So when you look at the image on the right, that is now classified as a frying pan. So what we did is we basically ran a adversarial machine learning algorithm where the two inputs were the original image, and we said, we don't want you to classify this as a penguin, we want you to classify this as a frying pan. What you see in the middle is the difference between these two images, but we had to amplify it by 100x in order to see it. So this image on the right, it looks identical to us as humans as the one on the left. There's actually slight differences in the underlying RGB values of the pixels that make the machine learning algorithm get completely confused. So this whole field of adversarial machine learning is about finding the flaws in the way machine learning algorithms work in order to get them to reach incorrect conclusions. And if you think about why an adversary in cybersecurity would want to do that, it's because they're generating the data that is ultimately sent to a machine learning model. So for example, if you're using machine learning as a malware classifier, is it malware or is it benign? If they can figure out what do they need to tweak in their application to get it to classify as benign, that will make their job much better. So where else might this cause problems in the physical world? Well, we have these new things today like autonomous driving. So one of the research projects my team worked on was, what could we do to fool image recognition as it pertains to things like street signs? And the way that we did this project was we started with digital. So we started with a machine learning algorithm that would classify a stop sign as a stop sign, but then we used the same type of algorithm to figure out what is the perturbation required to create an adversarial image. And just as with the penguins, there's really no difference or very little difference to the human eye, but what the image classifier now sees it as, it's a speed limit sign. And think about an autonomous driving vehicle pulls up to a stop sign, it doesn't see it as a stop sign, and it drives right through. So the question you might be asking is, okay, it's great to do it digitally, but could you do it physically? And that was the next thing that we did. So instead of manipulating the images themselves with digital manipulation, we started researching, and we've actually progressed a lot since I put these slides together, where now it's not nearly as profound, but we used an algorithm to figure out exactly where would we need to put stickers on a sign in order to, just as we did with the digital form, make the machine learning algorithm completely fall apart. So what you see here on the left is stop sign just without any modifications. It's really 100% being classified correctly as a stop sign, whereas by putting this one sticker in exactly the right location, it now sees it as number one, an added lane sign with an 81% confidence, and then a speed limit 25 sign as a 9% confidence. And what's really interesting when we do this demo live is I can take the regular stop sign and I can turn it, I can wave my hand in front of it, and it doesn't change the classifier from classifying it correctly. But it's when you know exactly how to change the image in such a way that will directly impact the underlying machine learning algorithm, that's where you're able to use this type of technology to make it fall apart. So why is McAfee studying this? Like we're studying it not really because we're going to get in the business of automated driving or autonomous driving or image classification, but we are in the business of detecting malware. And just like the rest of the cybersecurity industry, we are leveraging advanced machine learning capabilities to do things like malware classification. So taking some of the learnings by looking at adversarial machine learning on things like image classifiers, we're now looking at how could you apply that to malware classifiers. And we see that many of the same techniques work just as well. So if we have a malware sample that we've extracted features from that get fed into a model, we can use a very similar adversarial machine learning model to figure out what are the exact minimal perturbations required to change that in order to have it viewed as benign, because this is essentially what the adversary is going to do. We're also studying how do you defend against this, and there are a lot of interesting properties about adversarial machine learning that were a bit surprising to us until we really got into the details. Number one, there's this interesting property called transferability, which essentially means an adversarial attack on one type of machine learning will actually be effective on other types of machine learning. So that was counterintuitive to us at first because we were thinking of ways to defend against somebody using adversarial machine learning against us, where one of the naive approaches was, well, we'll just run a set of models and then take the ensemble results and make that our underlying classification. And that had issues because of this issue related to transferability. There are techniques that do work better. So one of the techniques that we're now using is you attack yourself. So you actually take your training set, and a portion of your training set you apply adversarial techniques to. And then when you train your model on a combination of adversarial samples and non-change samples, and that gives you a more resilient model because the model is now trained to be, at least to some degree, immune to those adversarial challenges. One of the other big challenges that the cybersecurity and actually the entire AI industry has is this issue around understanding why a model predicted what it says. In my trivial example that I started with volleyball players, it's very explainable. I can tell you exactly why the model predicted you are a volleyball player or you're not a volleyball player. But when you get into a deep neural network, and a deep neural network is saying, this is a dog, this is a cat, understanding why did it come to that conclusion is a lot more difficult. And if you think about things that are a lot more serious, the machine learning model says you have a very high probability of a serious disease that you might want to start getting treatment for. But the doctor can't actually explain what the underlying symptomology is that reached its conclusion. So understanding why machine learning is making the decisions or the predictions that it is incredibly important. It's an entire field called explainable AI or explainable machine learning, and there is a lot of nuance. And I wanted to start with an example. So I don't know if you can see this, but this is an example where at first glance it looks like a pretty good model. So this is a classifier that is predicting whether something is a husky or a wolf. And we see 6 images, and from an accuracy rate, it got 5 out of 6 correct. So pretty good model, right? Until you look at why did it classify things as husky or wolf. So one of the techniques that we can use in explainable machine learning is we can look at, in something like an image classifier, what were the underlying pixels that had the image make the decision that it actually made. And it turns out in this model, this was the underlying data that actually fed into the classifier. And I don't know if you, I see some people smiling, basically you didn't build a husky wolf detector, you built a snow detector. So In this case, if you look at the underlying pixels that were actually used in most of the images, it was really looking for how much white there was in the image, because the wolves were generally taken in pictures of snow and the huskies were not. So it was really an awful model and was not very good at all at distinguishing between the two, but because of the way the training set was set up, you could perceive that this was actually better than it actually is. So just in closing, and then I'm happy to take questions on really anything, is there is this notion that artificial intelligence is able to solve all sorts of problems, and that artificial intelligence is actually intelligent. And one of the things that I'm trying to point out to the industry is artificial intelligence is not really intelligent. It doesn't understand the context. At the end of the day, it's math, where it's models that are predicting outputs based on their inputs, but the context of those inputs is often not understood by the model. So in my field, we can have things that work very well when they're tested against things that we've seen in the past, but when we see something very new, they don't work nearly as well. We also need to recognize that there's a high level of fragility. The models are a lot more fragile than many people understand, and in many fields, it doesn't matter because there isn't an adversarial element to it. But in things like cybersecurity and things like defense, where you might be using artificial intelligence as part of a weapon system, where you do have an adversary, recognizing that the adversary is able to use techniques to confuse the model is absolutely key. And then finally, recognizing that the technology itself will make adversaries more effective. So AI will make adversaries more effective in being able to defeat some of our new technologies, to focus on things like finding victims to go after. They can use some of the same types of problems that AI is very good at, things like classification. So a cyber criminal can look at their sea of victims and say, out of all these victims, which ones are likely most vulnerable? And then those would be the ones that they would focus their attacks on. And recognizing that all of these things will make my industry, and hopefully many of yours, it's great to hear that you're adding a new focus area around security, really much harder. And one of the things that makes this industry a lot of fun to be a part of. So with that, I will take questions on anything.
So we've got a couple of mics. If you have a question, if you'll raise your hands, one of our ambassadors will bring the mic. And we just ask that you hold your question until you get the mic. That way we can capture it on video.
Okay, can I ask you questions if you don't ask me questions? Yeah, a question right here.
You mentioned how, like, now I guess with a lot of models, there's no appreciation of context. Do you know currently of like any research about like building context-aware models, and like how do you think that would change the security landscape for you?
So there definitely are models that attempt to comprehend context. So a lot of the deep learning models are trying to predict context. So for example, instead of having simple image classifiers that say it's a dog, it's a cat, it's a bird, it'll come back and say it's a dog jumping over a fence, and implying that it comprehends context. But part of the challenge that we're finding is the context is still very subject to the limitations of the training set. So inferring a new situation that has never occurred, that any of us as human beings would be completely obvious, are much more challenging than simply putting all the pieces together to have something that looks like context.
So you talked about like how you can trick these models into seeing other things, and how a part of avoiding that can be kind of almost like vaccinating against it by giving it the examples of these problems, and part of the data set would allow it to then be immune to that sort of. What's the best way to find what best attempts at the model to try to get it to be immune to?
Sure.
Is it a lot of brute force, or is it like, is there a method to the madness?
So it's at least we've used a lot of trial and error, and part of the good news, bad news, depending on how you look at it, is there are a decent number of open source adversarial ML libraries. So the one that we used for the Penguin was, I think it was Foolbox. There's other ones out there, and we've tried different algorithms. I think at some point, as the cyber criminals start using adversarial techniques more, we'll work towards optimizing our defense. Right now, what we're seeing in the wild is there's very limited use of adversarial techniques outside of academia and outside of research. So the good news is we're not impacted by it quite yet. We are trying to get in front of it. So right now, we're really trying to understand it versus optimize our vaccinations against it. But we will flip at some point in time.
So I was kind of wondering how vulnerable you think the automobile industry is to this type of attack, especially given like Tesla's trying to train their AI for self-driving cars. Couldn't that cause a lot of problems?
Yeah, so it's a great question, and I would put it this way. There's very little issue with random noise impacting the model. So one of the things that we found is the models are highly resilient to having random interference. So if you have a stop sign and a big cement truck goes by it and it gets a lot of dirt blown on it, like that actually doesn't all of a sudden make it look like a speed limit sign. But if there was a reason for an adversary to start messing with things like traffic signs, it could be very bad. I think that if adversaries had a reason to have a negative impact on things like autonomous driving, it would be bad. The good news is I don't think there are strong incentives to disrupt autonomous driving. You could definitely have kids, painting on stop signs dots in exactly the right place with infrared paint, and causing mayhem. But I don't know that that's much different than throwing nails and tacks or other things in the road. You could cause lots of mayhem today without self-driving cars. So out of all the things I worry about, it's something that we need to be aware of. And just like we're trying to immunize our malware-based detection capabilities, the autonomous driving industry should at least study this. But I don't think the incentives are there to tamper with autonomous vehicles as they are with other industries.
Right. Very interesting talk. So having seen the extent to which AI can be used from adversarial perspective, generally speaking, do you think it is the right time that there should be a regulation to which AI can be used, how it should be used, or there is a downside to a regulation? Should it be open source? How do you see as an expert to security?
So it's a fabulous question, and my opinion is it is just math. The technology is out there. The technology is well understood. And what we see with regulation is the legitimate businesses and organizations will follow the regulations. The bad actors will not follow the regulations. It's very similar to my view on should we regulate the use of strong encryption, where there's this big debate that's been going on for the past few years on things like should device makers put backdoors in things like phones in order to give law enforcement the ability to recover keys in the case of criminal or national security incidents. And Similarly, in that case, my perspective is bad actors, they can download application level encryption, applications that do encryption outside of the device. So putting backdoors into a device for law enforcement or other government officials is going to make it so that all of the innocent people are putting their privacy potentially at risk, while the terrorists and criminals will simply download strong encryption apps and still have their data unavailable to law enforcement. I think artificial intelligence is exactly the same. It's well understood, the techniques are already out there. So creating regulation to try to pull it back is really impractical. The other thing that I'll say on this that I think is a good point is we need to treat software differently than other forms of technology in regulation, in that you can build software out of nothing, right? So you can basically write an RSA algorithm in a couple of lines of Python, even if you have nothing to start with, which is very different than building an explosive device or a nuclear weapon, or even other forms of technology controls. To build high-performance semiconductors requires multi-billion-dollar fabrication plants that somebody just couldn't build in their garage. So thinking about software differently than other types of technology that we should consider regulating, at least in my view, is a very different ballgame.
We can say that humans have achieved intelligence over these years only because like we have been fetched this much amount of data right from the day we are born and all the analysis. So if we are fetching the same amount of data and analysis results to the computers, do you think that we could actually achieve true artificial intelligence?
I think that we sometimes fail to recognize how much of everything that we do is driven by things that we've learned, even very basic functions. So when we think about things like vision, there are cases where people who have been blind for the vast majority of their life regain their sight and struggle with things like seeing stairs as just a set of lines on the floor. And that's because their brain hasn't been trained to comprehend what the inbound images should actually be turned into in the physical world. So I do think there's this interesting question on when we think about artificial intelligence in machines versus the way that the human brain works. Like there's lots of research on putting the two together so that we can make AI think more like humans. But I also think we need to think about how humans actually learn is based on a number of different things, partially things that are inherent in genetics, as well as what they learn from environmental capabilities. And the complexity of the human brain is something that at least I don't see being possible in AI anytime in the very near future. It's one of the reasons in cybersecurity we believe that AI is very effective at helping with automation and some course level analytics, but we still need human responders to understand the context of complex situations and be able to reason and rationalize, especially things that have never been seen before. So I think we're still a ways away from the two really coming together. I don't know if I saw a hand or not.
If there are no other questions, thank you.
Thank you very much.